Hi there, this is David Williams from the Electronic Engineering Technology Department at Okanagan College, and today I want to talk about inductance and inductors. Now, as we know, when an electric current passes through a coil of wire, there's a magnetic field that's induced around that coil of wire. And we also know if the magnitude of the current changes over time, so will the strength of the magnetic field. And it just makes sense. If you have a stronger current, stronger magnetic field, weaker current, weaker magnetic field. We also know that if there's a change in the magnetic field through a conductor, then that conductor is going to induce a magnetic field that's going to try to oppose that changing magnetic field. But what happens when there's only a single current carrying wire in the system, so there's no other elements in the system to be affected? What's going to happen to the magnetic field in that single current carrying wire if that current is changing? Well, it turns out that the single current carrying wire will induce a voltage across itself that's going to create an opposing current to create a magnetic field that opposes the changing magnetic field caused by the original changing current. Now, this is kind of a crazy concept. We have these two complementary effects of electromagnetism and electromagnetic induction that are manifesting themselves simultaneously in the same wire coil, and this effect is called self-induction. And it's really not as complicated as it seems. Let's look at a couple of scenarios. So let's say we've got a wire. Let's say we've got to start off with a battery. Okay, so we've got a battery, and over here we've got a loop of wires. All it is just a loop of wires, and as we'll see in a moment, these loops of wires create something called an inductor, which has a certain amount of inductance in it. These are the concepts we're trying to work up towards. So we'll come back to definitions in a minute. But just remember that all this is a loop of wire. And what I want to do, before I do any of this, I'll make a break. I've got a break in the wire. So I've got this switch. Okay, so initially this current, this wire has no current through it because it's an open circuit. And since there's no current through the wire, there's no magnetic field anywhere. There's no magnetic field in the loop. There's no magnetic field in any of these wires. Now I'm going to close this switch. Now at the instant that switch is closed, there is no current that's created yet. And what actually happened is that current has to ramp up because it's going to take some energy to build up the magnetic field around this loop of wire. And this loop of wire is going to create a fairly strong magnetic field. And to get to, starting at 0 up to some magnitude of magnetic field, it's going to take a period of time to get to that ending magnetic field. And a couple of reasons that it takes that length of time. One, we're building up energy. You can't just put energy into the magnetic field instantaneously. And number two, when we close the switch, there's going to be an increase in current. That increase in current is going to create that magnetic field. And that changing magnetic field that we've created is going to induce a current, or induce an EMF, what's called a counter EMF. It's going to induce a voltage that's going to create a current opposite to the changing current that we're trying to create. So we've got two sort of explanations for why it takes some time for the energy to build up in this system. Now, let's go the other way. Let's say we have some current that's been flowing in this wire for a while. So the magnetic field that we see here is at its maximum strength. And now, somehow, we're just going to put a break in this wire. And we've got a lot of energy built up in this magnetic field, or I don't know how much energy. We've got some energy built up in this magnetic field. And it's got to go somewhere when we break the current, right? Because when we break the circuit, the current's going to go away. The energy in that magnetic field has to go somewhere. And what's going to happen? Well, what it's going to do, it's going to induce a voltage across this break. It's going to create a current across the break, and if it's a big enough voltage, you'll actually see some arcing take place as the energy from this magnetic field dissipates. So this concept of inductance is the capacity of a capacitor to store energy in the form of a magnetic field around itself due to the current that's through the field. And we actually have definition for it, well, I mean, the definition, I just told you what the definition is, but we can actually, we've got units for this capacity to store a magnetic field. And so it's going to store a magnetic field. The system's going to store a magnetic field. And the size of that magnetic field is going to depend on how much current is going through it. So we'll have, I should mix up my units here, my symbols here. So we've got magnetic field phi for a given amount of current. There's the end. I want to do an I there, not an A. Flux per current. And depending on the geometry of the system, depending on different things in the system, you're going to have a different amount of flux that's able to be created, a different amount of magnetic flux is created for a given amount of current. And that is referred to as the inductance, which we give by the letter L. The symbol for inductance is L. And the units for inductance are in henries. I always laugh at this unit because, well, I mean, it's named after a man named Henry, last name Henry, and I always laugh at it because we have all these other units, volts and amps and farads, which are all sorts of more exotic more exotic sounding names to me anyway. I mean, we've got these one unit that's called the Henry for inductance, which is a very common sounding name to me. So depending on the geometry, you're going to be able to have a different size magnetic field for the same amount of current. And for example, you might have a wire with 3 loops in it, and a wire with maybe 1, 2, 3, 4, 5 with 6 loops in it. Remember, each one of these loops is going to create a magnetic field within the inductor that's oriented along the loops. And the more loops you have, the more there's fields added together. So for the same amount of current, if the current is equal to 1 amp in this one, and the current is equal to 1 amp in this one, we're going to have magnetic field added 3 times here, and magnetic field added together 6 times here. So you're going to have a much stronger magnetic field created from the 6-loop inductor than you will have from this 3-loop inductor. I'm going to clear this screen and talk about the relationship between the voltage and the inductance and the changing current. So, inductance is equal to phi over I, or the flux over the current. If we rearrange this, inductance times current is equal to the flux. Now, if we take, because remember inductance and these magnetic fields are created by changing currents, or no, magnetic fields are created by currents, but if we have a changing current, we're going to have a changing magnetic field, which is going to induce a voltage. So if we're changing this current, and we're changing this current, we're changing this flux over time, we can take the time derivative, so what the rate of change of both of these over time. And the inductance of this inductor, of a system, or a circuit element, is going to be constant. So we have the rate of change of current times the inductance is equal to the rate of change of the flux. Now, it may not be quite so familiar, but imagine that we have another constant in here, in this whole system. We've got n. So n just being the number of loops. The number of loops of the wire. So, do you recognize what this is from? This n d phi dt, or n, the number of loops times the rate of change of the flux. This was Faraday's law, and it's saying that the induced EMF is equal to n times the rate of change of the flux. So if we rearrange or rewrite this equation, we've got this induced voltage going to be equal to the inductance times the rate of change of the current. And this is really the sort of fundamental definition of what inductance is. We're going to induce a voltage that's dependent on how quickly you're changing the current times what the inductance of the circuit element is. Now let's look at a couple of really simple examples here.
We're going to look at a few circuit examples that are highlighting the equation here. The induced voltage is going to be equal to the inductance times the rate of change of the inductance, rate of change of the current, sorry. And if we know those two values, the inductance and the rate of change of the current, then it's pretty easy to figure out what the induced voltage is. But to figure out the direction of the induced voltage takes a little bit of thought. But all you have to do is just remember that the inductor is going to oppose any change of current by creating that voltage, that induced voltage. And so you can think of the induced voltage as another source in the circuit that is trying to push current in the opposite direction as the external change of current is going. The tablet driver is not running. Yes, it is. I'm using it right now. Here's the first example. We've got a voltage source connected to a resistor, and here's my inductor. And let's say we're able to manipulate this voltage source to increase it. So what we're going to be doing is changing the current. We're going to deal just with conventional current here. I think it's easier with inductors to deal with conventional current. And so we have this current. It's going in this direction. And now we're changing the current. We're increasing it. So we're actually trying to increase the current that's going in this direction. And in order to oppose that current, we're going to induce a voltage on this inductor that opposes that current. So if we were to opposing a change of current, remember the delta I is also in that same direction. So the change in current's in that direction. So we want to try to we're going to have this current that's going in the opposite direction. And if this is a source right here, in order for that source to have current going in that direction, the voltage polarity must be like that to create that delta, that opposing current to go in that direction to oppose the changing current. So the chain of effects in this particular circuit is if you increase the source voltage, didn't label it, let's call that the source voltage, that's going to lead to an increase in current, which is going to cause an induced voltage, and of course is equal to the inductance times the rate of change of the current. And then we determine this by figuring out the direction that a current would be, we would need to create a current to oppose this changing current. And what about going the other way? If we've got basically the same circuit setup, the source voltage with a resistor and an inductor over here. I'll call this the Vs. Here's my resistor and my inductor. And instead of increasing the voltage, we're going to be decreasing the voltage here. So the current is still going in this direction, but our change of current, we're decreasing it, so our delta I is in that direction. And now this inductor is going to try to oppose this delta I, so trying it's going to induce a voltage will be induced across here to create a voltage that would create a current opposing this current. So if this is we treat that as a source to oppose that current that's going upwards, we're going to have a source that's going that way that would create a current going that way. So sort of adding on to the current that already exists, but we're opposing this delta I that's decreasing. So we can figure out the polarity there. And now pretty easy to figure out what the magnitude is. Let's say, for example, this inductor is 500 millihenry. And we know that if we know the di dt, we can just plug it into our equation. So if the di dt, let's say, is equal to, I don't know, what would be a good number? 10 amps per second. So we're decreasing it rather quickly. I guess that would be a negative because we're decreasing it. So the induced voltage is going to be equal to the inductance, so 0.5 henries times 1 amp per second. We get an induced voltage of 10 amps per second. Negative 10 amps per second. So this is an induced voltage of 10 volts. The magnitude is going to be 10 volts. It's negative 10 volts because of the way the current's changing. But what does negative really mean in this instance? Well, we still should go through this exercise of figuring out the induced voltage like we just went through here. Now, one more example. I'm going to clear this again. Let's imagine we've got the same voltage source, or similar voltage source, that's just connected directly to this big electromagnet here. And let's say I'm standing here, grabbing on to both sides of this electromagnet. So I got these really long arms that are grabbing onto both sides of this electromagnet. Now, somehow the circuit gets broken. We open the circuit up somehow. It just gets snapped off, or the electromagnet just gets quickly disconnected from the battery. Now, when you have this sort of instantaneous break in the circuit, the current's going to go from some amount of current flowing in the circuit to zero almost right away. So the dI/dt for this type of situation is going to be really big. And let's say, let's put a number in there, a really big number, 1,000 amps per second. So it's going from, let's say, an amp down to 0 in a millisecond. So we've got a rate of change of 1,000 amps per second. And let's say this is a really big electromagnet that's got an inductance of 1 henry. So the induced voltage is going to be 1 henry times 1,000 amps per second. And induced voltage is going to be 1,000 volts. So I'm holding on to both sides of this electromagnet, so I'm going to have 1,000 volts across my, basically across my body, which is probably going to shock me. Now, the good thing about this situation is there's only a certain amount of energy that's stored in that electromagnet, and once all that energy in the form of the electromagnet, the form of the magnetic field, is dissipated, then there's no more energy to shock me. So very quickly there's this induced voltage of 1,000 volts, but it dissipates quite quickly, and I'll feel a quick shock, but it won't last for very long.
Okay, a couple more quick things about inductors before we get into some more details of the way inductors behave in circuits. And the first thing I want to talk about is energy in an inductor. And I've mentioned that the magnetic field that's created is storing energy. There's energy stored in that magnetic field. And we want to quantify how much energy is actually stored in there. And this actually requires a little bit of calculus, but we're going to sort of skip over those steps and just give you an idea, a general idea of how calculus is involved without actually going into the mechanics of it. So we're going to start off with energy in an inductor. And the way we're going to figure this out is to start off with looking at what power is. And in general, in electrical circuits, power is equal to current times voltage. And remember that in an inductor, we're trying to figure out the energy in an inductor. So an inductor equals, the voltage is equal to the inductance of the inductor times the rate of change of the current. So power is going to be equal to I times L times the rate of change of the current. And in general, energy, how much energy is used by a system or created by a system, I use those terms loosely because we're not violating any laws of physics. We're not supposed to be violating any laws of physics here. But the energy is going to be equal to, how much energy is used in a particular time is going to be equal to the power over that time times the time. And as if it's a constant power, that's going to be true. But in general, it's going to be equal to the integral over time from time 0 up to some time of the power. So the power may be constant, it may be a changing thing. And in our case, it's not a constant, it's definitely a changing thing, so we have some changing current there. So if we're to do the integral over time of I times L times the rate of change of the current with respect to time, we'll go through the mechanics of that, but what we would come up with is the energy that's in an inductor is going to be equal to 1/2 times the inductance times the current squared. So that's energy in an inductor. The last two things I want to look at for just general things about inductors are inductors are actual circuit elements. Right? Here's a picture of some of them, some inductors. So just wires wrapped around, usually wrapped around some kind of ferromagnetic material, iron. They can also sometimes be air core, so it's just a wire wrapped around nothing. So you can imagine it would be this loop, but without the iron core inside it. And of course, if you've got an inductor and you're putting it in a circuit, you can put multiple ones in a circuit. You can connect them in series. So here's you've got one inductor, two inductors, three inductors connected in series. We'll call that L1, L2, and L3. And if we wanted to know what the total inductance was across all those inductors, well, we could figure it out. And actually, I want to leave that as an exercise for you to figure out, but the total inductance is going to be equal to L1 plus L2 plus L3. And to give you a hint of how to derive that, I want you to remember, keep in mind two things. These inductors are in series. So the current through L1 is going to be equal to the current through L2, equal to the current through L3. And since they're in series, and the other thing that we can figure out because they're in series is if we were to measure the voltage across the whole thing, so the voltage between that point and that point, that's going to be equal to the voltage across L1 plus the voltage across L2 plus the voltage across L3. So keep in mind those two things, as well as the fact that the voltage across an inductor is equal to the inductance times the rate of change of the current. You should be able to use those three facts to figure out or to prove that that's true. Now what about inductors in parallel? Now this is where we have 1, 2, 3 inductors. What we want to do is figure out the total inductance across these. This is L1, this one's L2, this one's L3. What's the total inductance across that? The total inductance is going to be equal to 1 over L1 plus 1 over L2 plus 1 over L3 to the minus 1. So 1 over L1 plus 1 over L2 plus 1 over L3, and then take the inverse of that number, and that gives you the total inductance of inductors in parallel. And using similar clues to what I did for the series circuit, but you'll have to figure out what the slight differences are because our circuits have got inductors in parallel. I want you to be able to derive this, be able to prove that this is true. Okay, and if you have any questions, you can talk to your instructor. We'll talk to you soon.